When you think about, like, stress testing a suspension bridge, right?
Mm.
You don't just look at it from a mile away and say, yeah, it looks sturdy.
Right, absolutely not.
You really have to zoom in incredibly closely on the steel cables. You're searching for these microscopic stress fractures.
Because that's where the failure starts.
Exactly. You're looking for the invisible wear and tear that happens deep within the structure long before the bridge actually shows any visible signs of weakness or sagging. And, well, human athletes are exactly the same way.
They really are.
You can't just ask a player, hey, how are your legs feeling today, to know what's really happening inside their muscle fibers. You have to look at the microscopic structural integrity of their actual cells.
Which is, we are entering a really fascinating landscape here because the human body is incredibly adept at masking the immediate biochemical costs of extreme physical exertion.
Yeah, and today we're looking at a study that proves exactly why pushing an athlete to do just a little more work can secretly poison their cells for days without them even realizing it.
It's a huge blind spot in how we train.
To guide us through this invisible world, we are diving into a study titled, How Does Altering the Volume Load of Plyometric Exercises Affect the Inflammatory Response, Oxidative Stress, and Muscle Damage in Male Soccer Players? This was authored by Jian, Tian, and Miao from the School of Physical Education at Henan University. And it was published in the Journal of Sports Science and Medicine in March 2024.
A really recent and honestly groundbreaking paper.
Okay, let's unpack this. Our core objective today is to understand how simply changing the actual number of jumps an athlete does alters their body's biochemical stress response. And spoiler alert for you listening, the results heavily contradict that old-school coaching mentality of, more work equals more damage, which equals more growth.
Yeah, the whole no pain, no gain thing. So to set the foundation, we are looking specifically at plyometric training here.
Right.
Anyone familiar with elite soccer conditioning knows plyometrics are absolutely vital for explosive performance, improving vertical leaps, rapid changes of direction, and sprinting speed. But the magic, and honestly the danger, relies entirely on the stretch shortening cycle.
Which is that highly dynamic sequence where a muscle rapidly lengthens and then immediately contracts, like the deep loading phase in your legs right before you violently leap off the ground.
Exactly. That expeditious eccentric movement, so the lengthening braking phase, is succeeded by a swift concentric movement, the explosive shortening phase.
Okay.
So when you land from a maximal jump, your quadriceps execute a massive eccentric action just to dissipate the kinetic energy, right? So your knees don't just buckle.
Right, like catching your own body weight falling from the sky.
Yes. And that specific braking force generates extreme tension per unit of active muscle mass. It forces a tremendous athletic adaptation, but, and this is key, it causes severe microtrauma to the skeletal muscles.
Specifically the fast twitch ones, right?
Yeah, the type 2 fast twitch muscle fibers and the structural Z lines that literally hold them together.
So if we want to measure that microscopic damage, how much trauma did these researchers actually inflict on these athletes?
The methodology was incredibly rigorous. They recruited 40 young male soccer players with identical training backgrounds, and they divided them into 4 distinct groups to test different volume loads of maximal effort vertical counter movement jumps. So the low volume load group performed 100 jumps.
Wow.
The moderate volume load group performed 150 jumps. The high volume load group executed 200 jumps. And finally, there was a control group that stayed in the lab but did 0 jumps.
Okay, I have to jump in here because classifying 100 maximal vertical jumps as the low group sounds wild to me.
It does sound like a lot.
I mean, to the average person, 100 max jumps is an insane volume. But in the realm of elite strength and conditioning, 100 jumps per session is actually the established baseline prescription for producing positive performance adaptations, isn't it?
Yeah, it is. It's the standard foundational dose for an elite athlete. The stimulus required to trigger adaptation in a highly trained soccer player is vastly different from, like, a recreational gym goer.
Right, so it's essentially like looking at a prescription medication.
Exactly.
The 100 jumps is the established recommended dose to get the physiological benefit. What this study is really doing by pushing groups to 150 and 200 jumps is effectively testing what happens when you overdose that prescription by 50% or even 100%.
That's a great way to look at it.
We're watching what happens to the human body when you take double the recommended dose of plyometrics.
And to isolate the effects of that specific overdose, The researchers just clamped down on every possible variable. The athletes had familiarization sessions a week prior, so their biomechanics were perfect.
With quite what?
They were forced to rest entirely from physical exercise for 7 full days before the test. They arrived after a 12-hour fast.
Yeah, and I noticed they also strictly monitored their diets for 3 days prior using nutrition analysis software. They were tracking exact intakes of calories, proteins, and specifically vitamin C and E. Why those 2 vitamins?
Well, because vitamin C and E are potent dietary antioxidants,
Well-
the researchers were planning to measure oxidative stress in the blood. If one athlete ate a massive bowl of berries loaded with vitamin C the morning of the test, that dietary antioxidant could artificially suppress the biochemical markers of oxidative stress.
Which would just completely skew the data.
Completely. And during the actual test, rest intervals were locked to exactly 1 minute between sets. And even the lab's temperature and humidity were fixed.
So it's incredibly controlled.
Very.
So if the 200 jump group has essentially taken double the dose, I would expect their legs to practically fall off. Let's look at the blood work. Did the physical damage actually reflect that massive overdose of work?
This is where we look at the biomarkers of exercise-induced muscle damage, or EIMD.
Okay.
Blood samples were drawn at rest, immediately post-exercise, and then at 24, 48, and 72 hours later. Across all the jumping groups, they saw the expected significant spikes in delayed onset muscle soreness, that classic DOMS.
Right, the feeling of not being able to walk downstairs the next day.
Exactly. But they also tracked creatine kinase, or CK, and lactate dehydrogenase, LDH.
And for you listening, CK and LDH are enzymes that are supposed to stay safely tucked away inside your muscle cells to help produce energy.
Yes, they belong inside the cell.
So when they show up floating around in a blood draw, it means the walls of the muscle cells have literally been physically torn open, leaking their internal contents into the bloodstream.
It is undeniable chemical proof of structural trauma. For all jumping groups, these structural damage markers peaked between 24 to 48 hours post-exercise.
Okay.
And alongside this, the researchers tracked the biomarkers of inflammation, which is the immune system's response to that specific microtrauma.
Wait, so the study notes a massive spike in leukocytes and neutrophils?
Yes.
Those are white blood cells. You're saying the athlete's body is reacting to a heavy workout the same way it reacts to a systemic infection or a disease.
The immune system doesn't really differentiate between a pathogen and massive mechanical trauma. It just recognizes cellular destruction. The white blood cells rush to the site of the microtears to essentially engulf and clear out the cellular debris. The researchers also measured an immediate violent spike in interleukin-6, or IL-6.
Which is what exactly?
It's a powerful pro-inflammatory cytokine acting as an alarm bell. Interestingly, those specific immune cells and the IL-6 return to their baseline resting values within just 24 hours.
But the inflammation cascade didn't stop at 24 hours, right?
Yeah.
Because that initial burst of IL-6 triggers a secondary reaction in the liver.
Correct. The liver receives that IL-6 signal and begins pumping out C-reactive protein, or CRP.
Okay.
So while the initial white blood cell count dropped back to normal quickly, the CRP levels continued rising. They peaked at 24 hours post-exercise for all the jumping groups.
Okay, so every athlete who jumped sustained microscopic muscle tears and triggered a full-blown immune system flare-up.
Right.
But here is the data point that absolutely stopped me in my tracks. When you look at the charts comparing the 100 jump group to the 200 jump group, the difference in muscle damage and inflammation is almost non-existent.
What's fascinating here is that, statistically speaking, it was not significant.
Really?
Yeah. I mean, there was a microscopic visual trend. The 100 group had marginally less damage than the 150 group, who had marginally less than the 200 group.
But not enough to matter.
Mathematically, no. Doubling the mechanical workload to 200 maximal jumps did not cause significantly more structural muscle tearing or acute inflammation than doing the baseline 100 jumps.
It completely defies our basic intuition about physical load and cause and effect. Like, here's where it gets really interesting.
Yeah.
If doing double the physical work doesn't result in double the muscle damage or inflammation, a coach might look at this and think they found a loophole.
Oh, absolutely.
If the structural damage to the muscle fiber is basically the same, why not push the athlete to do 200 jumps every single time just to get the extra 100 reps of skill practice in?
Because that coach would be looking at the wrong markers. The standard markers of structural muscle damage hit a plateau, but the real penalty for that overtraining was hiding somewhere else entirely. It wasn't in the mechanical tearing of the muscle fibers, it was in the oxidative stress. This forces us down into a much deeper cellular level of analysis.
The hidden cost of high volume. Okay, let's break down these oxidative stress markers because they initially sound incredibly dense.
You do, yeah.
The study tracked 3 specific things in the blood: 8-OHDG, MDA, and PC. We need to explain exactly how this works.
Let's define the mechanism of the threat first. When we exercise intensely, especially with those brutal eccentric braking movements, the muscle rapidly consumes oxygen.
Okay.
This often creates a temporary anoxic state, so a microenvironment lacking oxygen. When blood rushes back in, the metabolic processes generate a massive amount of free radicals and reactive oxygen species, like superoxide anions.
Right.
These are highly unstable molecules missing an electron. They will violently rip an electron from anywhere they can find one. When these free radicals overpower the body's natural antioxidant defenses, we enter a state of oxidative stress.
They're essentially cellular vandals.
That's a perfect word for it.
Which brings us to the first marker, 8-OHDG. The study identifies this as a biomarker for oxidative DNA damage. So these free radicals are so aggressive they are bypassing the outside of the cell, penetrating the nucleus, and literally damaging the genetic instruction manuals inside the athlete's cells.
That is precisely what 8-OHDG represents. It is a modified base that gets excreted when DNA is repaired after being attacked by reactive oxygen species.
Wow.
So the more 8-OHDG in the blood, the more the athlete's actual genetic material has been battered.
That's intense.
The second marker is MDA, or malondialdehyde. This indicates lipid peroxidation.
Okay, let's unpack lipid peroxidation. Our cellular membranes, the literal walls keeping the cell together, are constructed of lipids, specifically polyunsaturated fatty acids.
Exactly. So when those free radicals attack the lipids in the cell membrane, they cause a chain reaction of degradation.
Like weakening the walls of a house.
Yeah, the walls of the cell are chemically compromised, releasing MDA into the bloodstream. So an MDA spike tells us the actual structural boundaries of the cells are being chemically eroded.
And the third marker, PC.
PC stands for protein carbonyl. This measures protein breakdown via intracellular degradation pathways. When oxygen radicals flood the cell, they physically attack the amino acids that make up the muscle proteins,
Leaving behind a chemical scar called a carbonyl.
Yes.
So finding PC in the blood means we are finding the charred wreckage of the athlete's own muscle proteins.
That's exactly what it is.
You have markers showing DNA damage, cell wall degradation, and protein breakdown. And here's the breakthrough finding of the entire study.
Yes.
Unlike the muscle damage markers that plateaued, volume mattered massively when it came to oxidative stress.
The moderate volume load of 150 jumps and the high volume load of 200 jumps resulted in significantly higher levels of 8-OHDG at 48 hours and significantly higher levels of MDA all the way out at 72 hours compared to the baseline 100 jumps.
So doubling the jumps didn't tear the muscle fibers significantly more, but it actively poisoned and degraded the cellular DNA in the cell membranes for 3 straight days.
Yes, it's a huge hidden cost.
But there is a crucial nuance to how the body handles this overload. It wasn't a linear increase, was it?
No, it wasn't. While 150 jumps and 200 jumps caused significantly more oxidative damage than 100 jumps, there was no statistically significant difference in the oxidative damage between 150 and 200 jumps.
Wait. So jumping from 100 to 150 spikes the DNA and cell wall damage, but adding another 50 jumps on top of that, going to 200, doesn't spike it further.
Right. The researchers propose that the human body has a stimulation threshold for oxidative stress.
Okay.
The oxidative system's response maxes out at a specific range in this case, at that moderate volume of 150. Any additional mechanical load beyond that threshold simply cannot cause a greater biochemical response.
Because it's already maxed out.
Exactly. The mechanisms generating the free radicals and tissue damage are already operating at absolute maximum capacity.
It's essentially like trying to get a tan in the sun. At 30 minutes, representing our 100 jumps, you get a tan. It's the optimal dose for adaptation. If you stay out for 2 hours, representing the 150 jumps, you get a blistering, terrible sunburn. Your skin is damaged.
Yeah.
But if you stay out for 4 hours, the 200 jumps, you don't technically get a double sunburn.
No.
The top layer of your skin's pain and inflammatory response is already maxed out at the 2-hour mark. The damage is just being pushed deeper and deeper into the cellular level, preventing any chance of rapid healing. The body literally cannot register more surface alarm bells. The system is just overwhelmed.
That perfectly illustrates the stimulation ceiling.
Yeah.
The biochemical alarm system is entirely overwhelmed.
We have all this rich, complex biochemical data now, We understand the DNA damage, the cell membrane disruption, the threshold ceilings. But how does this change the way you, the listener, or a professional coach, actually approaches a week of training?
If we connect this to the bigger picture, the practical application for sports professionals, coaches, and really anyone engaged in high-intensity training is stark. The study definitively shows that the lower volume, the 100 jumps, is the optimal dose. It provides the necessary mechanical stimulus to tear the Z-lines and improve explosive performance.
But without the poison.
Exactly. It avoids those devastating, lingering spikes in DNA and cell membrane damage, the 8-OHDG and MDA, that persist for 72 hours in the higher volume groups.
And we need to emphasize that even at the optimal dose, recovery is not instantaneous.
Not at all. Even in the 100 jump group, their creatine kinase levels, that enzyme leaking from torn muscle membranes, remained elevated for 72 hours.
Wow.
This emphasizes the absolute vital need for strategic periodization in any training program. You cannot just program heavy plyometrics every other day.
Which brings up a massive trap for athletes. An athlete might walk into the gym 48 hours after a plyometric session and say, "Hey, coach, my DOMS is gone. I feel totally fine. My legs are fresh. Let's go hard again."
It happens all the time, but their blood profile is telling a completely different story. Their subjective feeling of soreness has subsided because the initial inflammatory white blood cell rush has passed. But at a microscopic level, they are still experiencing massive cell membrane disruption and DNA stress.
So they aren't actually recovered.
No. If a coach ignores the biochemical reality and prescribes another high-intensity session based only on how the athlete feels, they're pushing that athlete straight toward overtraining syndrome.
So what does this all mean for you? Even if you aren't an elite soccer player lacing up your cleats on a Tuesday morning, understanding the science of this study validates a crucial fitness principle. More is not always better.
It really isn't.
Your body's oxidative stress response has a literal mathematical ceiling. Pushing past your optimal training volume doesn't grant you better physical adaptations. A coach prescribing extra practice might think they're building a tougher athlete, but this blood work proves they're actively destroying their player's DNA for the next 72 hours without giving them any extra muscular benefit.
It proves that physiological recovery isn't just about resting your muscles until they stop hurting. It is about allowing your cellular structures and your actual genetic material the necessary time to repair the unseen microscopic trauma.
Let's do a quick recap to pull all these threads together.
Yeah.
The researchers found that doing 100 maximal plyometric jumps will give a soccer player the necessary structural training stimulus.
Right.
Pushing that volume to 150 or 200 jumps won't significantly increase their structural muscle tearing or their acute inflammation, but it will drastically increase oxidative stress, actively damaging their cell walls and DNA for up to 3 full days.
The human body is incredibly resilient, but it operates on a delicate biochemical ledger. And this raises an important question for us to consider.
Yeah.
This study measured a single acute training session. We saw what happened over a 72-hour window. But think about a professional soccer player over a grueling 9-month season. If that oxidative stress ceiling is hit repeatedly, week after week, match after match, does the body eventually build an oxidative shield, upregulating its own internal antioxidants to adapt to that constant barrage of free radicals?
Or is it the opposite?
Right. Or is that slow, unseen accumulation of DNA and cellular membrane damage the exact mechanism that leads to the infamous mid-season burnout, where a player's performance inexplicably drops off a cliff and injuries suddenly spike?
That is exactly why we have to look past the surface, down into those microscopic stress fractures we talked about at the beginning. You can't fix a crumbling bridge if you don't know the steel is quietly wearing out from the inside.
Beautifully said.
To really grasp the science and see the exact biochemical charts, oxidative markers, and recovery timelines we discussed today, we highly encourage you to read the full article. That's How Does Altering the Volume Load of Plyometric Exercises Affect the Inflammatory Response, Oxidative Stress, and Muscle Damage in Male Soccer Players? By Jian, Tian, and Miao. Make sure to follow the channel and turn on notifications so you never miss our next scientific deep dive. Keep learning, and we'll